Functions are often visualized as a line on a graph, and this line shows how the value returned by the function changes based on the changes in the input value. For example, suppose the function f is used to calculate the number of meters travelled by a cyclist in a given number of seconds. Here's a chart for this function, which shows how far the cyclist has travelled on the y-axis against the time taken on the x-axis. Now we can measure the slope of the line by dividing the change, or delta, in y, which in this case is f of x, over the change in x. And that will give us the speed, or more accurately the velocity, of the cyclist. We calculate the deltas by taking 2 points on the line, subtracting the y and x values from the 2 points, and then dividing. So in this case we can take the points 3 by 5 and 2 by 4. And that gives us deltas of 1 and 1. Now 1 divided by 1 is just 1. So the rate of change, in this case the cyclist's velocity, is 1. And as you look at the slope of the line on the graph, you can confirm that as we travel 1 in the x direction, we go up 1 in the y direction. Our cyclist is travelling at 1 meter per second. So we can find the velocity of our cyclist if we assume they're travelling at a constant speed. But what if the function for distance travelled in a given time looks like this? When we look at the chart for this function, you can see that it's curved. The cyclist is not travelling at a constant speed, they're accelerating. Well, we can find the average rate of change over a part of the function by drawing a straight line. It's called a secant line, and it joins 2 points on the function line. Then we can calculate the slope for the secant line. In this case, our points are 4 by 17 and 1 by 2, which gives us deltas of 15 and 3. 15 divided by 3 is 5, so the average velocity between these points on the function line is 5 meters per second. And sure enough, for every x unit along the secant line, we increase y by 5.